Good morning. So let's be back to our lecture. It's time already, so we base on our the So in our previous lecture, we have talked about the discovery of atom. What could be the concept of the atom, and what would the main principle experiment help us to discover electron, and then discovering photon and neutron that make the structure of the atom. Okay? And we talk about the isotope, we talk about the concept of electron, how the evolution of the atom can be. Okay? So this morning we will start half of the important lecture before we have a middle. We talk about the electronic structure of the atom. When we see the letter electronic structure, that means how the electron will arrange in the atom, right? So when we learn about in our previous lecture about the structure of the atom, we understand that one atom can have only one electron, for example, the atom of hydrogen. Okay? But you can have also some other atoms which have several electrons. For example, lithium, you have 3 electrons, sodium, you have 11 electrons. So let's consider first the case of only one electron. So you have nuclei, you have electron runs around. Okay? But then, how this electron runs around the nuclei? What could be the distance between the nuclei and electron? Okay, so even for the case of only one electron, we have several questions. And then for the case of several electrons, where the only electron will have the same orbit, that means the same distance to the nuclei, and they will move by the same way. Or you will have some electron move farther from the nuclei and some gets closer from the nuclei. Okay? So in our previous lecture, we just know about the atom. We have electron, nucleon. In the nucleon, you have neutron and proton, and the electron runs around. But then we don't know exactly how the movement of electron will be in the case of only one electron, and in the case of several electrons, how the electron will distribute. Okay? So the objective of this morning lecture will be understanding how we can describe the movement of electron and what could be the consequence. Okay? So here we remember that we start from something very unclear imagination, philosophy about the structure of the atom. And then we get progressively. So starting from today, we will talk about this structure, okay? Yeah, the modern one, how the electron will run around the nuclei, and if you have several electrons, how they arrange. And then we talk about the concept, not moving in the precise orbit, but moving in the space by the random way while we move the orbital. So you will learn about the concept of orbit and orbital. Okay? And of course, all of the movement of electrons we want to describe because we want to understand how the arrangement of electrons will impact on the physical and chemical property. Because at the end of the day, we want to look at the physical and chemical property of the matter. So here are the main content. First, we discuss about the electronic structure, the arrangement of the electron in atom. Second, we talk about electron and energy. Why all the time we need to consider about energy? Because we say that the driving force of our progress, of all our action, come from energy. When you have a higher energy, that means you are more active, but also less stable. When you are at a lower energy, that means you are more stable and then less active. Okay, so all the time we talk about the energy, so we will see what could be the relationship between the electron, the arrangement of the electron, and its energy. And we talk about the concept of orbital, so I invite you guys to think and to distinguish between orbital and orbit. So orbit is something precise with the precise distance, and if something moving in orbit, you know the rate, the velocity, you know the time, you should be able to predict what could be the position of the matter. But orbital is that you cannot know precisely the position of the matter, but you can know only the probability that you find the matter. Okay? And then we talk about the electronic configuration, the arrangement in the layer by layer, and we talk about the relationship between electronic structure and physical and chemical property. Okay? So here, the split one, where you see that you have nucleon made of neutron and proton, and you have electron runs around. So to start the thing easily, we will consider first the atom of hydrogen. We have only one electron, right? We examine first the simplest case, only one electron, and then we will see what will happen when you have second electron or when you have more than two electrons. So, here we have a concept of continuous spectrum. Continuous spectrum is a guide rainbow, all the color with all the wavelength possible. Okay? From the source wavelength 200 nanometer to very long wavelength. Okay? For example, when you see the rainbow, you see 7 colors, right? Because they correspond with at least 7 different wavelengths. Okay? From the ultraviolet to the red one. So, the thing is following. Imagine that you have one nucleus. The case of hydrogen, right? You have one nucleus, positive charge. And you have an electron which is negative charge. It runs around. And you know that between the positive charge and negative charge in the classical physics, it will have interaction, right? The interaction will be the attractive interaction. So the two matter, two particles, one positive charge and one negative charge, they will interact to get to attract to get this closer one another, right? So they tend to get closer. Okay? So imagine that you have a positive charge, you have an electron by this distance. So first you have one movement, okay? And then this guy gets closer because of attractive force, right? And then it moves, and then it gets closer, move, it gets closer, it moves, and then at one moment there is no more distance between positive charge and negative charge. That means by the classical physics, you can imagine that the electron negative will get closer, 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 and then get sink into the nuclei, and the atom will disappear. Okay? But when you have one atom, you keep in vacuum, it will be stable forever. That means the electron moving and get closer and collapse with the nuclei will not happen in reality. So the concept of classical physics, the interaction between the positive charge and the electron negative charge will be not applied for this kind of atom. Okay? Then the second thing is that you have the law of conservation of energy. Imagine that here you have energy 0, nuclei. You have an electron here at a higher potential energy, right? And then it gets closer, that means it gets to a lower energy, and lower energy, and lower energy, and become 0. Okay? When you get from higher to lower energy, because of the law of energy conservation, you will emit some energy, right? Is it correct? So, first, when you move from this state to this state, you will emit one energy. You emit one color, for example, the violet. But if you jump to this level, you will emit another level, which is short UV, for example. So by moving continuously like this way, to sink into the nuclei, you will emit continuous spectrum with all the wavelength possible. Do you understand it? So it means that if you excite one nuclei and get the atom moving like this, it will emit a kind of solar spectrum if you want. You will see from the UV until the red or far red spectrum. Is it clear or not? So that we expect from the classical physics. If you apply the classical physics to the structure of the atom with the electron moving around the nuclei, positive, you have two phenomena. First, it should emit a continuous spectrum with all the wavelengths. Okay? Second, at one moment given, the atom will disappear because the electron will come to the nuclei and it's collapse. Is it clear? Okay. But in reality, the atom is stable. It will not disappear. So, first evidence to say that the classical physics is not applicable to the case of the atom. Second, instead of having continuous spectrum in the case of hydrogen, you have emission of only this wavelength, this wavelength, this wavelength, and this one. In between the two, you cannot see any emission. So instead of having one continuous spectrum, that means you have only few wavelengths emitted. So you see that the second evidence to say the classical physics is not applicable for the atom structure. Am I clear in my explanation? Okay? So for the case of sodium, for example, you see only the emission of near to 600 nanometer. There is no continuous emission. You will not see anything at 400 nanometer. So the two evidence to say that in principle, the classical physics is beautiful, but will not applicable for the structure of the atom. Not only the physical property have some specialty, but the chemical property also have some specialty. For example, you know that helium and argon are inert. Inert in the sense that if you put in oxygen, it will not react. Okay? However, if you take lithium, sodium or potassium, you expose to the air, it will react rapidly, generate a lot of heat, and it becomes flammable. So it says that the atom of the hydrogen and the atom of lithium will be not, the atom of helium and the atom of the lithium will be not identical. In the sense that the electron in the helium, somehow they are at low energy. And the electron in the lithium, they are at higher energy. Because I mentioned that if you are at higher energy, you tend to be active. So the reaction with oxygen becomes rapid. But if you are at extremely low energy level, that means you are stable and you will not react easily. So it says that if you pick up 2 electrons from helium and 3 electrons from lithium, you will not have the same arrangement. Right? Some will at lower energy level and other at higher energy level. So how we can describe all of this? The arrangement of electrons become extremely important because the classical physics will not be able to apply and to describe the structure. And then the chemical property also has something special we need to explain. Is it clear? So you see that, for example, in terms of the property, if you take sodium, it can be cut easily, very soft. And it reacts violently with oxygen, so that's why we need to keep in the kerosene oil to prevent the contact with oxygen. And if the expert will come in very soon, right? It will have all the beautiful balloons, but they will fill with the inert gas, helium, because they are extremely stable. That's something you can see in the lab. So, the conclusion, the remark will be, not all the electrons will be arranged in the same manner around the nucleus. Some at the lower energy and other at the high energy make different in terms of chemical reaction. Now, so this is a little bit mathematics, right? Back to the case of hydrogen. You have only one electron. Imagine that here you have the nuclei of the hydrogen with one proton. Okay? And here in this point, you have electron which stand far from the nuclei and it moves around the nuclei. So you can describe the position of this electron by using this spherical coordinate, right? So you can describe this point by x, y, and z, okay? And also the angular. So basically, if you have a proton here and electron here, at this position, right? The electron can run like this, okay? This can also run like this one. So it can run like this way and can run like this way as well, okay? So you can describe the movement of electron around the nuclei by using this spherical coordinate, okay? So basically you have two directions. You can move surround, so we can describe by this vector. You can move this one, you can describe by this vector. But if this guy, instead of moving like this or moving like this, it will move like this one. Okay? So get shorter, longer. So basically it will change the distance between the electron and the nuclei. Okay? So basically you change the dimension of the atom. Okay? So basically you have a three possibility of electron movement. Okay? So when the spectrum with a few light emission of the hydrogen has been discovered by experiment, one scientist named Rybert, he discovered a formula, this one, purely mathematical, to describe precisely the emission of the light spectrum of the hydrogen. So basically, if you take the N1 and N2, any interval number, where N1 have smaller value than N2 for sure, right? Because it will not have emission with a negative value. And this value is a constant named Ryber's constant, right? And what R for name Rybert, and H represent for the case of hydrogen. Okay? So this constant is 1.009 blah 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 7 discovered by Rybert. And if you put any value of N1 and 2 here, you will have the emission lambda of the hydrogen. And with this very simple formula, Rybert can describe precisely the emission spectrum of hydrogen, matching perfectly with the experimental measurement. So you see how that explains also why here, even you are chemists, even you are biologists, you need to learn mathematics, right? Because the spectrum of the hydrogen experimentally measured is something done by the physicists. But to explain, to describe the emission, if you can make up, if you can propose a very simple equation like this, it will be perfect, right? You guys can be easily to predict what could be the emission. Okay? So, by using this formula, we put N1 and 2 different, you put the constant, Ryber's constant here, you can explain the first, second, third, and fourth spectrum line. Okay? Any question? So, 10 minutes already, we need to stop to go back. Here is the question. The electron transition from N1 equal to 3 to N2 equal to 2 correspond to the following emission line of hydrogen atom. Which one? A, B, C, D. Which one? Quick.
câu hỏi.
Okay? Can you pick up first the ripple constant? Okay? So, this is the question. So, the ripple constant is here. This one. Try to calculate.
5,6,7 nhân 10 như vậy.
Hả? Từ
Đó, em xem cái bước sóng.
A, B, C, or D?
D.
Huh? D, right? Everyone done?
Yes.
Very simple, right? You put R1, R2, and then you know what happened. So basically here you have this one, and 3 and 2 corresponding with 6, 5, 6, so the answer will be D. Okay? So imagine that if you pick up N1 and 2 to N1 from this one, we will have equation of 122 nanometer. If you pick up from here to here, you have 6, 5, 6. And if you have from N4 to N2, we calculate it will have 486 nanometer. So very simple one, right? But simple one means very simple formula, simple equation, mathematical equation can explain perfectly the case of emission of hydrogen. Okay? So, we have experimental emission spectrum of hydrogen with few light. We have a Ripple equation. But Ripple equation does mathematical equation. There is no physical mean behind. Okay? Then people try to understand how can we explain the few light emission and what could be the physical mean behind the equation described by Ripple. So, it's come to the model of atomic spectrum proposed by Niels Bohr. Bohr family is quite special because Niels Bohr and his fish both received Nobel Prize for physics. The father and son get 2 Nobel Prize, quite special. You have also the family of Curie. So Marie Curie and her girl received 2 Nobel Prize in physics. Marie Curie got Nobel Prize in chemistry. So, we talk about the model proposed by Bohr. Bohr assumed first that the law of physics, we call the classical physics, will not applicable, not appropriate to describe the atom structure. So we mentioned about that. So to explain the nice picture of hydrogen, Bohr relied on several assumptions, hypotheses. Okay? First, the electron moves around proton in a circular orbit, like this. Okay, that's the first assumption. Later, for sure, we understand that it's not correct, right? But at the time, early 20th century, proposed by Bohr, is circular orbit like this. Orbit, not orbital. Okay. Second, only orbits of certain radius, certain distance from the nucleus to this, correspond to certain defined energy are allowed. That means, he said, you have nuclei, you have electron, circulate. But it do not circulate in any distance. Only few distances are possible. Like N1, N2, N3, but not N1, N1.1, 1.4, something. Not continuing like that. Okay? Only few distance corresponding with exact different energy are allowed. Is it clear? So that you can say that okay, electron circulates surround in the precise orbit, and if you take the nuclei, you can see that the radius, I mean the distance from nuclei to this orbit, will have several precise distance, and when you have electron in this, it will have exact energy, so you cannot expect an electron from somewhere in between. Is it clear? Next. An electron in a magnetic solar orbit have a specific energy that we call allowed energy state. It also means all the states in between are not allowed, or we call forbidden. Okay? Tương đối cấm. Number 4 assumption. An electron in an allowed energy state will not radiate energy and therefore will not spiral into the nuclei. Wow, he said exactly to solve the problem that the classical physics requires. For example, we say that in the classical physics you have an electron, it will move, and when it moves like this, it will radiate energy, it lost energy to get closer to the nuclei, and at one moment the electron and the nuclei will collapse. He said that if the electron stands in allowed energy state, it will move, but during the movement like this, it will not emit any energy, that means it will not lose any energy, so it will not get closer to the nuclei. Okay? Number 5. Energy is emitted or absorbed by the electron only as the electron changes from one allowed state to another. Let's say, imagine that if you have an electron here, at this allowed energy state, moving to this also allowed, from higher energy to lower energy, it will emit energy. Okay? In the inverse way, if the electron stands here at lower energy, it gets excited here, it will need to absorb energy to move from this lower to the higher one. Okay? The electron here cannot move in between and cannot emit anything except in between the two allowed states. Is it clear? Okay? Easy to understand, right? So then, Bohr proposed a calculation, because he said that if you have atom, you have nuclei, you have electron in allowed energy state, it will have a precise energy, right? So how can we calculate this energy? So he proposed this equation to calculate the energy of this electron when it is in the number 1 allowed state, n equal to 1, or in the second energy state. Is it clear? Okay? So here in this equation you have S equal to Max Planck constant, C is speed applied, and R is Rydberg constant. So you can see here that by this equation, Bohr proposed energy will have a negative value. It has negative value because the energy represents the attractive interaction between the nuclei and electron. Okay? So that we call the bound state, that means the bonding state. If you want to remove electron, you need to put energy inside. So the energy you need to put in will have a positive charge. So it means the energy of the electron itself will have a negative value. Okay? It means the electron stand in the atom will be stable if you want to pick it out. So later you do the ionization, right? You move one electron to become gas ion, you need to put energy. So by doing so, from the Bohr model, you can recover the Rydberg equation, right? So you take two energy level. When it moves from N1 to N2, the energy emitted will equal to the different energy between two levels. So you will find the emission line exactly described by the Ribos equation. Is it clear? Huh? Yes or no?
Yes.
Easy to understand, right? So if you play here, you have N1, you have N2, and here you have N2, that means you have P2, here you have P1. So when the electron here come back to this and emits the photon, that means the energy of this photon is equal to delta E equal to E2 minus E1, right? So you know E1, E2 by the Bohr model, so you can find the lambda here by this equation. It's quite easy. You do the calculation. Okay. So electron can change from one allowed state to another allowed state. That's described by Bohr. Okay? So to increase energy, that means from E2, lower energy to E1, you will need to receive energy. So if you have one photon which have energy perfectly equal to different energy between the E2 and E1, the electron from here will get excited to the E1 level. Okay? Let's say you have E2 here, lower state, and E1 at higher state. If you pump a photon with enough energy, the electron will absorb the energy from photon and excite. Okay? So E2 equal to E1 plus energy from the photon. That's the law of energy equation, conservation, right? In the inverse way, if you have electron at higher energy, the higher one, like this, it sinks to the lower energy, it will emit photon, right? And the photon emitted will have energy equal to the different energy between the E1 and E2. Is it clear? So, if you want to excite it, you put energy inside, right? And when you get the emission, I mean polar, you will emit energy. Just easy to understand. Okay? Now, just because of conservation of energy, so the photon will equal energy photon equal to E1 equal to minus E2. It's quite easy to understand. Now, question. In a normal circumstance, even atom X absorbs the photon lambda 1. It will emit the photon lambda 2 where A. Lambda 1 equal to lambda 2. Second, lambda 1 larger, longer than lambda 2. And 3, C, lambda 1 shorter than lambda 2. What could be the correct answers? So you imagine that you have two energy levels, right? You can absorb photon with the wavelength lambda 1 to get excited. Okay? And then we will be back to emit the lambda 2. Okay? So what could be the relationship between lambda 1 and lambda 2? Whether 1 equal to 2, 1 shorter than 2, or 1 longer than 2. Am I clear in my question? Yes. So what could be the good answer?
Ây, cái này chắc là A.
So energy equal delta E equal this one, right? So B.
A.
Who think the good answer will be A? Please raise your hand.
Em.
Only 2, 3, 4. 5, 6. Thank you. Who think the answer B? Thank you. And who think the answer C will be correct? Okay, thank you. So, right? First, you have one atom each, right? First, it will absorb number 1 to get excited. Okay? So, the number 1 is equal to the energy difference between this guy and this guy. Okay? Correct. And then the electron of this guy will be back. That means number 2. So the energy of the number 2 equal to difference between the two energies as well. So basically, you should expect number 1 equal to number 2. Right? Because of the law of energy conservation. So number 1 equal to number 2. However, in reality, when you do the experiment, when you do the measurement, you will not have number 1 equal to number 2. Okay? You will have number 1 smaller than number 2. Okay? Why? Number 1 smaller than number 2. That means the energy you emit will be smaller than the energy you absorb in, right? Is it correct? Right? So if you have number 1 smaller than number 2, it means that energy you absorb 1 larger than your energy you emit. Sorry. Well, yes. Yes. Right? That means you absorb more energy and you emit less. So, somehow you violate the law of energy conservation. So, where you lost energy? Do you understand what I mean? Huh? If you respect perfectly, you obey perfectly the law of energy conservation, the number 1 should equal to number 2. Is correct? Because you have 2 energy level, this guy gets excited, and then it will be back to exactly the same position. So you observe, it will release exactly the same. Right? However, I mentioned that in the reality, when you do the measurement, experiment, you will not have number 1 equal to number 2. But you have emission wavelength number 2 longer than the absorption wavelength number 1. It also means, because longer wavelength, that means smaller energy, right? So that means you absorb more and you emit less. That means you lost somewhere. So my question is that, where did you lose this energy? Because for sure, the law of energy conservation, you cannot violate. Huh? So, where did we lose this energy?
Well, I think some energy convert to the kinetic energy of atom.
This atom himself or another one? No. Thank you. Exactly. The thing is following. If I do the measurement for this guy, he's alone, only him in the planet. Okay? Then he absorbs electron, he will emit exactly the same. Okay? But the reality, you will never have only one atom. Right? You always have one atom beside. Okay? So let's say this guy, I bring this guy. This absorb energy, right? And then get excited at high energy. he get now a sponsor or scholarship, he become rich, right? He will tend to, basically, if he receive 40 million scholarship from USH, he could spend all of that, right? Right? Because of the law of energy conservation, the law of money conservation. Okay? So if this guy receive 40 million scholarship from USH, he can spend all for himself. So in that case, if he's alone, there no friends, no family, no girlfriend, then the amount of money he spent will exactly equal to the amount of money USDS sent to him. That means number 1 equal to number 2. But luckily, this guy is not alone. He have at least 2 guys beside. Say that, okay, I have a 40 million. Can we go to have some social activity? So he shared some of money for this guy to make this guy vibrate. Okay, excite the elite beat. Not the same amount of 40 million, but at least 1 million. So that means this guy give 1 million for this guy. Now he have himself only 39. So when he spent only 39. Because one make this guy excited already. So in terms of the atom, one atom get excited, if we interact with the atom beside, to make the atom beside vibrate like this. So that becomes the kinetic energy. And when it's moved, the kinetic energy is returned to heat. So basically the law of energy conservation will be the photon we absorb transfer to the kinetic energy, so the heat, plus the energy you emit. So more heat you generate, softer, smaller energy you emit, so longer wavelength you will emit. So in reality, you will have number 2 longer than number 1. Okay? So if you absorb UV, you will emit visible. If you absorb visible, you will emit near infrared or far infrared. Okay? Is it clear? Huh? Clear or not? So,
hơi đúng.
có hiểu không?
Đoạn
Okay. Cảm ơn. Okay, so basically, thing is that the conclusion. In the ideal case, you will have number 1 equal to number 2. In most of the normal circumstance, you will have number 2 longer than number 1 because you lost energy. Okay? Clear or not? Next question. Okay. Can we imagine an atom or compound X that absorbs photon number 1 and emits photon number 2 with number 2 smaller than number 1? In the normal case, we say that number 1 equal to number 2. Right? Ideal case, 1 equal to 2. Normal one, you have number 1 larger than number 2. Number 2 larger than 1. Here my question is inverse. Can you imagine that 1 absorbs the photon number 1 and emits photon number 2 with 2 shorter than 1? 2 shorter than 1. So you inverse like this. That means you will emit more than what you absorb in terms of energy. Can we imagine this case? Is it possible? And if it is possible, how we can do? If it is not possible, what is the problem? Do you understand my question?
Yes.
And trust me, it's not the imagination of form, it's reality. Okay? So people try doing this kind of thing in the physics. Can we make the situation where you have number 1 will be longer than number 2 to emit? That means you absorb less energy, but you emit more. Huh? Any idea?
Thật sự là mũi điện nhân.
First, do you think it's possible?
Yes.
If you say no, forget, right? If you think yes, then you find the way. Các khoa học gia, công nghệ gia. Đấy. Thế nào? Yes or no? Trong một lời công đạo đi chứ.
Yes.
Yes? How can we do? Remember that the law of energy conservation, we cannot violate. Right? So if you want to at least more, you should find somewhere more energy you input in the system. Right? Any suggestion? Anyone know about this? Okay, so let's move on. Here is diagram showing the energy absorption. Number one, so you get electron excited to the excited state at the higher energy level, right? If you want us the number 2 shorter than the number 1, that means the gap between the energy here and the excited should be larger, higher, right? So how can you absorb energy here, you get the excited state, but then when you get this, the electron become up to that. Any suggestion? Okay. You have a first energy gap. Electron get excited from this to this, right? That you have number 1 absorption. If you want to have number 2 absorption, admission shorter, that means more energy than energy absorbed. That means the electron excited should not stand here, but stand up there, right? So how can you bring electron? You excited from here to up there. And if you bring up there, it will be back. You admit number 2 shorter than number 1. Is it clear? Yes or no? So how the question is now? You are excited at this level, but you want, when you admit, this guy should come up here. Then how can we do?
I think we exercise 2 times.
Thank you. If it's excited and you pump a second photon, is excited second half, like this one.
Okay.
Okay? So basically you absorb 2 photons of lower energy, you emit 1 photon of the higher energy. The law of energy conservation, it will not violate. Okay? So that's we call, in the physics, we call 2 photon absorption or 2 photon excitation. You will have what we call the virtual state. 1 to excite, and then you pump the second photon with excite. Okay? Okay, so back to the Bohr model. There are many possible transitions between a lower state, but always the energy you emit or you absorb equal to the different energy between the lower and higher energy level. So all the time we will have a nice spectrum emit one precise wavelength, not a continuous wavelength. And you know this equation describing the energy at one lower state by Bohr, right? So imagine that if the n, so the n equal, later you know that the quantum number in the next part, the lecture, you know, when n equal to infinity, then you will have energy equal to 0. It means you have nuclei here, you have the first energy level here, okay? You excite, you excite. At one moment, the electron will get very far from the nuclei, and then no more interaction between the electron and nuclei. So you can consider now the electron become free, because the attractive force between the positive nuclei and the electron make the atom stable, right? And keep the electron stable. But if you excite the electron very far at the higher state, so when the electron get the n equal to infinity, then the energy of this guy becomes 0. That means there are no more bound energy with the atom, so electron now become free. Okay? So you can imagine that at that moment you can attract the electron easily. There are no more interaction with the nuclei. So let's say here you have energy, here you have energy, and here you have a principal quantum number. You can see that you start from quantum number 1, so the first layer after the nuclei, and the second one and so on. When the n equal increase to very high level, the energy becomes almost 0. So when the n equal to infinity, the energy equal to 0, that means you remove electron, so the hydrogen now get only one proton in the nuclei. So that you have the proton S+, right? Okay, so to summarize, Bohr model proposed an excellent success, at least for the case of hydrogen atom, one electron. Okay? But it cannot explain the spectra of other atoms. For example, start from the helium with 2 electrons, Bohr model has some difficulty. But at least Bohr model, the hypothesis, the theory proposed by Bohr, have 2 important useful ideas. First, electrons in atom have only certain discrete energy level. It should be not continuous. It has some fixed energy level. Energy is exchanged in moving an electron from one level to another one. We explained quite a lot in the problem. So I propose that we have 5 minutes break before we move to the second part to talk about the wave behavior of the electron, and we talk about the most model of the atom.
Quốc Anh ơi, chọn sách cao cả hôm nay giảng bài này hay nữa. trên là cái quả bóng rồi thì nó to như thế. Ở đây có đọc phát sóng rồi mọi người. Bắt đầu câu hỏi, từ câu hỏi phát sóng. Okay, never mind.
Thế các thanh niên nghỉ giải lao mà không đứng dậy vươn vai một chút là cứ ngồi chỗ nhé. Các em thấy, tại vì lại chuẩn bị làm thi đến nơi rồi, các em thấy phỏng vấn tuyển sinh vào trường thế nào? Dễ không báo?
Chào biết thế nào?
Hả? Dễ mà đúng không? Vui mà đúng không? Thầy thôi để có tỉnh thầy kể cho mấy đứa nghe chuyện thầy đi phỏng vấn. Cái năm đó thầy phỏng vấn một cậu, nó nhìn rất là năng động. Ở trường nào thôi thầy không nói. Thế vào thì có các lựa chọn đúng không? Có 4 option. Option đầu tiên của cậu đấy là ICT, 2 là Material Science, 3 là Biotechnology, 4 là Space Application. Thế thì thầy mới phỏng vấn xong thì thầy mới hỏi là 4 cái lựa chọn của bạn nó chả liên quan gì đến nhau ấy. Thế tại sao lại lựa chọn ICT? Thì rất thật thà các bạn, bố em bảo là cái này lắm việc nó cũng yên tâm, học xong là xin được việc. Thế thầy bảo thì đúng rồi, nếu mà đi cài máy tính thì đúng là có việc. Rồi. Thế thầy bảo thế lựa chọn thứ hai là Material Science thì ai bảo? Mẹ em bảo. Thế mẹ bảo thế nào? Dạ mẹ em bảo là bây giờ công nghệ nano khắp mọi nơi đúng không? Mẹ em dùng kèm mỹ phẩm mà toàn là nano hết. Nên mẹ em bảo là sau này là đấy là tương lai đấy. Thế là thầy mới đùa, thầy bảo cái công nghệ sinh học chắc là người yêu bảo đúng không? Đó, đúng rồi. Thầy đùa, đúng không? Thầy đùa, thầy đang expect ở trong đầu là nó bảo không, công nghệ sinh học là cái mong muốn của em. Thì câu chuyện nó khác, mà không đúng thôi. Thế thầy bảo sao thế? Thầy bảo hôm nay người yêu em cũng phỏng vấn một bio. Ok, thế thì đúng rồi. Thế mới hỏi thì chắc là Space Application thì chắc là lựa chọn của em thật đúng không? Tôi bảo không ạ. Thế lựa chọn của anh? Bạn em nó bảo là Space Application bây giờ công nghệ vệ tinh nó phát triển lắm, Viettel nó nhiều việc lắm, nên là em apply rồi. Ô, hay nhỉ? Đúng không? Rồi. Còn một chuyện nữa. Có một thanh niên từ trường Chu Văn An, ở đây có ai Chu Văn An không? Ok. Thế thầy thì thầy thích hỏi những cái câu hỏi sau khi mà hỏi chán chuyên môn thì thầy thích hỏi những câu hỏi nó vui vui một tí để xem mọi người hiểu thế nào. Tại vì quan điểm của thầy học đại học không phải để trong kinh nghiệm. Thế thầy hỏi mà Chu Văn An có cái đặc điểm rất là hay đúng không? Là rất là hình ảnh, tức là rất là gì đấy. Đi đến phỏng vấn là bao giờ cũng mặc cái áo vest mà có CVA đúng không? Chu Văn An đấy. Nhìn là biết là dân Chu Văn An. Thế thầy mới hỏi là học trường Chu Văn An đúng không? Vâng. Rất là tự hào. Thế thầy hỏi thế Chu Văn An là ai? Chu Văn An là ai? Có ai biết Chu Văn An là ai không? Thế thế là bạn ấy trả lời là cái này chắc là mọi người nghe học thuộc mà học không biết phải Chu Văn An học thuộc gì đấy nhá. Bạn ấy trả lời là Chu Văn An là người thầy đầu tiên của Việt Nam. Đúng không? Thế thầy mới hỏi cái gì các em vừa nói cái gì? Thì bạn ấy bảo là vâng, Chu Văn An là người thầy đầu tiên. Thế thầy mới hỏi ok, Chu Văn An là người thầy đầu tiên thì ai dạy thầy Chu Văn An? Thầy tự hỏi. Đúng không? Đúng không? Cái câu thật ở trong lịch sử người ta gọi là Chu Văn An là người thầy của muôn đời. Các bố học hồn bõm, các bố là người thầy đầu tiên. Thế người thầy đầu tiên thì ai dạy thầy? Đúng không? Tức là học văn ấy mà sao lại đang đọc literature như thế? Không đọc literature đã là một việc, nhưng mà đọc literature không hết nó còn nguy hiểm hơn, đúng không? Đau bụng phục nhân sâm ấy. Đi phỏng vấn rất nhiều chuyện thì lộ ái ố lắm, nhiều vui lắm. Có một trường hợp sợ nhất, nhưng mà sau đó bạn ấy không bằng đi học, tại vì thầy sau khi phỏng vấn xong ấy, cái thời bây giờ thì khó rồi, tại vì bây giờ già rồi, trí nhớ nó kém, với lại các bạn đông quá rồi. Nhưng mà cái thời mà trường khoảng 200-300 sinh viên, thầy chỉ dạy một lớp thôi, thì thầy thường là thầy nhớ mặt của các bạn mà thầy phỏng vấn. Thì thầy không thấy bạn ấy quay lại học thì chắc là bạn học trường khác. Thì bạn ấy đến phỏng vấn một bạn nữ, nó đến phỏng vấn cái hồ sơ, hồi đấy là còn in hồ sơ ra chứ không phải là hồ sơ số, in ra hồ sơ phải dày như thế này, hồ sơ của bạn ấy nó phải dày như thế này, các loại giấy khen, các loại giấy khen, đúng không? Từ cấp 1 đến cấp 2 đến cấp 3 các bạn dùng giấy khen lắm. Mà học nó đăng ký vào MST, Medical Science and Technology. Bố là bác sĩ, mẹ là bác sĩ. Thế thì các thầy cô ấn tượng lắm, phỏng vấn ấn tượng lắm. Đến thầy Phong hỏi, thầy Phong hồi đấy chưa là chủ tịch hội đồng. Thầy Phong hỏi thầy chỉ buồn miệng một câu thôi. Thầy nói là hồ sơ của em nặng thế nhỉ? Thế là nó học, không dỗ được nữa.
Con gái, ok.
Bình tĩnh.
Con gái chưa bị đánh nhau.
Bình tĩnh.
Bạn sắp sửa bị đánh.
Nghe này, cụ Phan Châu Trinh đã nói rồi, bất bạo động tắc tử, bất bạo động giả ngu, tức là đừng có bạo động là chết, đừng có bạo động là ngu. Ok, thôi đùa thôi. Cái thầy nói thế nó khóc luôn, sợ quá, đưa nước cho bạn ấy vẫn khóc. Thôi bình tĩnh đi, vẫn khóc. Các em đứng dậy ra ngoài thì quay lại vẫn khóc. Thế sau đấy mình hiểu là nó có vấn đề. Xong rồi để cho bạn ấy bình tĩnh lại thì bảo thôi em đỗ rồi đấy, không phỏng vấn gì nữa đâu. Thôi em đỗ rồi đấy, nhưng mà không phải phỏng vấn gì nữa đâu. Nhưng mà bây giờ phải cho thầy biết là tại sao lại xúc động thế, có vấn đề gì đằng sau ạ? Thì bạn ấy kể thật, bạn ấy nói là nhà bạn ấy con một, hai bố mẹ đều bên bác sĩ bệnh viện lớn, được chưa? Và bố mẹ bạn ấy đi communicate với mọi người là cô này chắc chắn đỗ trường y, không thể trượt được, tại vì là cả một hồ sơ dày như thế, tức là từ nó sinh ra nó chỉ biết đi thi, chẳng biết làm gì khác đâu, có nhiều giấy khen lắm. Thì tức là bố mẹ đã đi nói với các bạn từ năm nay thi chắc chắn là trường y là cô này phải đỗ đa khoa là no problem, đúng không? Nhưng mà càng gần đến ngày thi ấy, lúc đấy là tầm tháng 3, tức là khoảng tháng bình thường hồi đấy tháng 5 tháng 6 thi. Bắt đầu khoảng đến tháng 3 là bạn ấy bị stress và bạn ấy bắt đầu đặt vấn đề về bản thân ấy, tức là không tin tưởng vào bản thân thực sự, trong khi là cái expectation của bố mẹ nó rất là cao. Thế và thầy mới hỏi là sau khi mà bạn ấy nói như thế thì thầy mới hỏi là thế hôm nay em đến đây chuyển sang tiếng Việt luôn, khỏi nói tiếng Anh. Hôm nay em đến đây phỏng vấn là bố mẹ không biết, đúng không? Vâng ạ. Bố mẹ em, đối với bố mẹ em chỉ có trường y, trường đại học, không còn trường khác là trường đại học ở Việt Nam. Ok, đúng rồi, chắc là cũng đúng đấy em ạ. Nhưng mà thế tại sao đến đây các bạn? Tại vì nếu mà con trượt trường y ấy thì con phải có một cái ngành gì đấy nó liên quan đến y học để học. Thế thầy mới giải thích, nhưng mà MSc nó không phải là practical doctor, nó không phải đào tạo ra bác sĩ. Đấy, nó bảo và đến khi mà giải thích cho nó MSc không phải là practical doctor, không phải là học làm bác sĩ nữa, thì bắt đầu không dừng nó lại khóc được nữa. Và giải thích là thực sự là nếu như bây giờ nó thậm chí nó nói đến câu này mà thầy xong đấy về là thầy phỏng vấn xong về là tối không ăn cơm và mất cả tuần buồn, là bởi vì bạn ấy nói là nếu mà con không đỗ trường y chắc chỉ có cách chết, làm gì mà khổ thế con, đúng không? Mày vào làm bác sĩ còn khổ hơn nữa chứ, đúng không? Đồng ý không? Đồng ý không? Tại vì nhá, làm bác sĩ nhá, nếu mà làm bác sĩ là một cái nghề bác sĩ nghiêm túc ấy, thì có nghĩa là không có được tiền đâu, nước nó bình thường mà, đúng không? Còn đi làm thêm, làm theo kiểu under table thì thầy cũng nói, đúng không? Nhưng mà một người bác sĩ giỏi mà làm việc nghiêm túc ở trong bệnh viện rất vất vả, đồng ý không? Làm gì có giờ giấc đâu, mà đặc biệt là nữ còn con cái nữa chứ, đúng không? Thế thầy mới hỏi là bây giờ con đặt lại vấn đề gì? Bây giờ thôi mình không phỏng vấn, no rồi, chắc chắn đỗ rồi, đừng có lo nữa, đỗ rồi. Đó. Thế nhưng mà bây giờ nếu như các bạn, nếu như mà em học bác sĩ giỏi lắm thì em được như mẹ em, đúng không? Đúng không? Thế rồi em lại như mẹ em, rồi em cũng giỏi lắm, lấy một ông chồng bác sĩ khác rồi làm khổ một đứa con khác như em, đúng không? Thế sao không có phần mai đi? May quá mà lại trường học không biết nó đi đâu. Thật sự là rất là sợ, nên là sau khi mà tốt nghiệp mà sau khi mà các bạn thi tốt nghiệp xong, công bố điểm xong, thầy chia sẻ thật là thầy mất rất nhiều tuần chỉ để đọc báo dân trí xem có đứa nào tự được không. Nghiêm túc luôn đấy. Tại vì bọn em tưởng tượng là một người thầy sau khi mà đi phỏng vấn như thế về nó ám ảnh kinh khủng luôn. Còn một trường hợp nữa thì rồi thầy giải tiếp. Nó vào hỏi cái gì đó. Vâng. Thầy nói luôn, một ngày em chơi điện tử bao nhiêu tiếng? Nó bảo em thỉnh thoảng có chơi. Thầy nói bao nhiêu tiếng, không nói thỉnh thoảng có chơi. Nó khoảng 4 tiếng, thầy nói 4 tiếng không ra được như thế này, nó phải trên 8 tiếng. Okay. So, just for fun, wake up, okay? Now, we move to the second part. We talk about the quantum physics. So we use the Bohr model based on the understanding of classical physics. We describe the movement of an electron is precise orbit around the atom. Then, but Bohr have one important assumption, saying that the electron will move in some discrete energy in some precise orbit, right? But he could not explain why that's one assumption he could not explain. And on another problem, another issue that he cannot use his model to explain the spectrum of other elements, other atoms with more than 2 electrons. For the hydrogen electron is perfect, but more than 2 electrons could be enough. So then it's come to the time where Louis de Broglie, a French scientist, make following assumption. We know that the photon can behave as a wave, but also can behave like particle. Okay? So it means that if the electron behave as a particle, it can also behave like a wave. Okay? If photon itself is a wave, but also behave like a particle, then the electron, which is a particle, can behave also like a wave. And you know, for example, when you learn classical physics, you have a wave like this, okay? Then you cannot know exactly the position of the wave, right? It's like this. So, this idea starts. So, you see that Louis de Broglie proposed any particle, when it moves, it will emit a wave with the wavelength lambda by this formula. Okay? So you have the mass of the object, you have velocity, so how fast the object moves. So if you pick up the equation, you calculate for one electron moving at the rate of 10⁻⁶ meters per second, very fast. Then you will see that it will emit, it will correspond with a wave of 0.15 nanometer, so 1.5 angstrom. 1.5 angstrom we can observe. Okay? So it associates the movement of electron associated with a wave, but we cannot detect because it's too soft. Okay? So the wave property of matter are proved by a number of experiments. We will not go into detail. So maybe very fun calculation. Can you calculate the wavelength associated to your movement? Given that you know the mass, how fast you can move, right? Try to do it at home. So, based on the proposition of the Royce wave matter, we have some certification to Bohr model. And then it comes to the contribution from Heisenberg, Schrödinger, and so on. So we can calculate now with the Schrödinger equation, we can calculate the wave function of the system like Ada. So I will not go into that because it's very physics. So some main feature, the wave cannot be precisely localized. It's normal, right? If you have a wave like this, you cannot know exactly the position. An electron behaves like a wave, so it cannot be precisely localized. So it's, we can say like anti-proposition by this Bohr, right? Bohr says that the electron will migrate, move in a precise orbit. But here, because electron behave like particle, but also behave like a wave, so at a wave, electron cannot be precisely localized. Okay? So more precisely, we cannot know both the speed and the position of electron. The Heisenberg incertainty rule. That means if you know about the speed, you don't know about the position. If you know about the position, you don't know about the speed. Okay? You cannot know both. It will be like this in physics. So they are described by wave function, which give the probability of presence of some portion of space and energy. So that means instead of saying that electron moving in the orbit, and at any moment I will know exactly the position of the electron, I now can only predict what would be the probability I can find electron at this position, but not 100%. Okay? Let's say, if you have a satellite, right? A satellite will move around our planet in a given orbit, right? So at any moment, we know exactly where the satellite is. Okay? If we don't know the satellite is, then it will be in trouble. We know exactly with the movement rate like this, exactly at any moment we know exactly precisely the location of the satellite. Then in the Bohr model, if the electron moving in the precise orbit like this, we would know also exactly where the electron will look like at any moment. That means at any moment we can find electron with 100% probability at this position. Okay? But now, because the electron behaves like a wave, we cannot know precisely the position of electron. So we can only say that I have 90% of probability to find electron in this area, but I don't know exactly the position. Is it clear? So basically, to find the probability localize the position of electron, we need to solve this equation. And this equation, I can tell you that not so many people understand, even in Vietnam. Okay, not only at yet. Difficult to solve. So that's mathematics, very difficult one. But this one, much easier to understand. Like, instead of saying that here you have the nuclei, okay? Then electron moving at this orbit and this orbit, we say that the electron can move anywhere around the nuclei. And the density of this dot represents the probability to find electron. When the density of the dot more higher in terms of density, higher density of the dot means you have a higher chance to find electron in this area. Okay? It also says, if you pick up the nuclei here, the electron will look like here with a high probability. But when you go to this distance, the probability to find electron gets lower. And if you go there, you have very less probability to find electron. But even you still find it. If you go up to this distance, the probability to find electron gets almost zero. Okay? So instead of having precise orbit, we now decide that electron can stand any position in the space around the nucleus. We cannot know exactly the position of electron, but we can predict the probability to find this electron in this position. Okay? Is it clear or not? Chỗ này hơi trừu tượng thì có hiểu không?
Giải thích tiếng Việt cho an toàn. Đó là Ê Việt cho an toàn.
Ok. Những người làm truyền hình, đúng không? Đài truyền hình Việt Nam, nếu mà họ muốn thu sóng, họ muốn phát sóng, thì họ phải biết chắc chắn là cái vệ tinh của họ nó đang ở chỗ nào, đúng không? Đồng ý không? Nếu như các em tưởng tượng trái đất của chúng ta là hạt nhân của nguyên tử và cái vệ tinh đấy là cái electron, thì thực tế là cái vệ tinh này nó đang di chuyển theo một cái quỹ đạo xác định gọi là orbit, được chưa? Và với một cái tốc độ mà khi người ta phóng lên người ta sẽ định hình cho nó, được chưa? Thế thì với một cái tốc độ cố định như thế, với ở một con orbit, một cái khoảng cách từ bề mặt trái đất lên cái quỹ đạo như thế, người ta đã biết trước cái tốc độ, biết trước khoảng cách, thì ở bất cứ thời điểm nào một người kỹ sư công nghệ vệ tinh họ cũng sẽ định hình được là cái vệ tinh của họ đang ở cái tọa độ nào ở trên không gian, đồng ý không? Tức là bất cứ khi nào sếp hỏi, ê, vệ tinh của mình đang ở chỗ nào, nó sẽ nói chính xác 100%, không sai được, đúng không? Sai là chết, sai mất việc, ok không? Thế thì theo cái quan điểm của Bohr ban đầu ấy, là electron nó cũng chạy xung quanh hạt nhân theo những cái quỹ đạo như của cái vệ tinh đấy. Thế thì các cái electron đấy với cái tốc độ di chuyển đã biết, đúng không? Thì ở bất cứ một thời điểm nào Bohr cũng phải chỉ ra được electron nó đang nằm chỗ này, đúng không? Nhưng kỳ thực là electron nó không nằm ở một vị trí cố định như thế. Bởi vì thứ nhất là Bohr không giải thích được là tại sao electron nó chỉ nằm ở những cái chỗ cố định như thế. Thứ hai, về mặt thử nghiệm là cái giả thuyết là electron nó chỉ nằm ở những chỗ cố định như thế, nó chỉ đúng giải thích được cho cái phổ của hydro, phổ một electron, đúng chưa? Nhưng mà đến những cái phổ phát xạ của những nguyên tử nhiều hơn một electron, từ 2 electron trở đi, là mô hình của Bohr không giải thích đầy đủ. Tức là về mặt thử nghiệm đang đặt ra vấn đề là mô hình của Bohr không có đúng nữa, đúng không? Còn nữa là các em tưởng tượng nếu mà cái electron nó chạy, nó ở đúng các vị trí như thế, giả sử khi nó ở vị trí này mà em ném một cái hạt electron khác ở vị trí khác thì nó sẽ không tương tác được với cái hạt electron ở vị trí này, đúng không? Nếu nó đang cái satellite của em đang ở mặt bắc mà em bắn tên lửa về mặt nam thì cái satellite nó sẽ không dụng, đúng không? Nó không va chạm được, đúng không? Đồng ý không? Thế thì hiểu theo nghĩa là một cái electron mà nó chỉ chạy như thế, nó sẽ chạy đúng những cái vị trí mà chắc chắn như thế, thì bất cứ khi nào em lấy một cái electron khác em ném vào cái nguyên tử đấy, thì cái charm cái electron mà em ném vào nó va đập vào cái charm của cái electron của em đấy, nó gần như bằng không. Đúng không? Cũng như là cái tên lửa nếu mà nó chỉ ở một cái vị trí đấy, bố bắn ở các vị trí khác thì chắc chắn nó không trúng. Tuy nhiên thực tế là gì, khi mà em có một nguyên tử ấy, em vứt một cái electron vào thì cái charm mà cái electron nó scatter lại, nó bắn lại, nó rất lớn, đúng không? Hiểu theo nghĩa là cái electron của nguyên tử bản thân nó không nằm ở những vị trí cố định. Đấy là vấn đề experimental, ok không? Thế thì làm sao mà giải quyết được cái đấy? Thì có một cụ riêng rất là đẹp tên là Louis de Broglie. Cô ấy bảo là cô ấy nói rằng là gì? Cái photon ánh sáng ấy nó vốn là sóng nhưng mà nó có cả tính hạt, đúng không? Đúng không? Thế thì cái electron ấy nó vốn là hạt, cũng phải có tính sóng chứ. Tư duy nó cũng rất là logic, đúng không? Thế nếu mà electron có tính sóng thì các em biết rồi. Bây giờ ông ném cái viên đá xuống nước, ông sẽ tạo ra một cái sóng, đúng không? Ông có biết chính xác cái sóng ở vị trí nào đâu? Nó rất nhiều các cái đỉnh maximum và rất nhiều đỉnh minimum mà, đúng chưa? Thế làm sao biết là cái sóng nào là chỗ này chưa? Thế hiểu theo nghĩa là nếu với quan điểm là electron có tính sóng thì cái vị trí của electron là không cố định, Đúng chưa? Mà cái vị trí của electron không cố định thì làm thế nào tìm được nó? Thì người ta lấy cái hàm sóng lên, người ta bình phương nó lên thì nó ra cái gọi là probability, là cái xác suất tìm thấy nó ở trong không gian. Được chưa? Thế và người ta mô hình, người ta vẽ cái hình các cái xác suất tìm thấy một cái electron ở trong không gian ở trên cái hình như thế này, trên cái đồ thị như thế này, thì người ta thấy được là gì? Khi mà cái xác suất tìm thấy electron càng lớn, tức là cái density của những cái dot này càng lớn đấy, thì có nghĩa là cái electron đấy more or less nó ở xung quanh đấy thôi. Được chưa? Thế nhưng mà nếu như bây giờ em hiểu theo nghĩa là nếu như em muốn tìm cái electron ở vị trí này, đó, tại vì density of state, density, cái probability của nó rất lớn, cái mật độ của nó rất lớn. Nếu em muốn tìm electron ở vị trí này thì hiểu theo nghĩa là trên 90% em sẽ tìm được nó. Hiểu không? Hay hiểu theo một nghĩa khác, nếu bây giờ ông lấy electron, ông ném vào chỗ này, ném vào chỗ điểm này, thì 90% là cái electron của ông sẽ va chạm quay trở lại. Hiểu không? Thế còn nếu như mà ông muốn tìm electron ở cái điểm này thì lúc bây giờ nó chỉ còn lại 10% thôi. Hiểu theo nghĩa bây giờ ông ném một cái electron vào cái vị trí này thì chỉ 10% nó bật lại thôi. Đúng không? Còn nếu mà bây giờ ông muốn tìm electron ở chỗ này thì cái xác suất nó gần như bằng không, nhưng nó không bằng không. Được chưa? Nếu mà em tìm ở chỗ này thì gần như bằng không, thì bởi vậy cho nên là nếu như bây giờ em ném cái electron vào cái vị trí này thì nó đều chạy qua hết và cái ảnh em chụp lại nó đen xì. Understand? Có hiểu không? Không hiểu thì kệ. Okay? So, the space where you can find high probability of electron, we get the space around the nuclei where you have high probability to find electron, we call orbital. Okay? So instead of using orbit, now you're using the orbital. That means instead of saying that we find 100% electron here, we can say that we have high probability to find electron in this position. So we go orbital. You can ask me what would be the high probability? 50%, 60%, 90%? And what you want. But cannot 100%. Okay? So the space around the nuclei where you can have high probability to find electron, we call orbital. Okay? So that's the concept of orbital. So X orbital basically describing the space around the nuclei where you find electron. So you see that you will need to describe this orbital by first the size of the orbital, right? Whether the space you find it small or big. Okay? So to describe the size of the orbital, so the energy of the electron in this orbital, we use the first quantum number, we call the main quantum number n. Okay? Second, what could be the shape in terms of morphology, whether it's sphere, it will be square or whatever. Then we use the second quantum number, we call the momentum quantum number. Okay? And then if you have the orbital B like this, what could be the direction? Whether it's in the X, Y, or Z, we use the third quantum number. So basically, X orbital will be represented by three quantum numbers, N, L, and ML. Okay? So, the position, that means the big size, the small or big, and whether the shape, spherical, square, will be 1, L, and what could be the direction of the orbital. First, we talk about the principal quantum number, N, which will have the integral number all the way positive integral value. So if n increase, the orbital becomes larger, the electrons spend more time far from the nuclei, and the electron have higher energy because it gets higher level, and the electron will less bound to the nuclei, so it becomes more active. It's easily to get removed. Okay? So L, angular momentum quantum number, has integral value from 0 to n-1. So let's say if you have the main quantum number n equal to 1, so L have only one value, 0. But if you have n equal to 2, that means L you have two values, 0 and 1. So you have 0 until n minus 1 value. So this angular momentum quantum number defines the shape of the orbital. So the orbitals are named as S, B, D, F, depending on the value of momentum quantum number. L equal to 0, you have orbital S. 1, you have orbital P. 2, you have orbital D. And 3, you have orbital F. So there are 4 orbitals that you know for the moment. Okay? We have the magnetic quantum number describe the orientation of the orbital in the space. Because in the space you have a coordinate, a spherical coordinate, right? You have x, y, z. Okay? So what could be the direction of the orbital on the x, on the y, or on the z? So describe the orientation of the orbital is have integral value between minus L to positive L, including the 0. It says if you have orbital S, that means you have L equal to 0. So you have only one value, right? Minus 0 is 0. So you have only one value. But if you have one orbital P, so that means L equal to 1, then the ML will accept the value minus 1, 0, and positive 1. So you have a 3 value of ML. That explains why orbital B, you have 3 orbital B and oriented in 3 directions. One on X, one on Y, and one on Z axis. If you have L equal to 2, so basically you have orbital D, right? Then ML accepts the value minus 2, minus 1, 0, positive 1, positive 2. So you have 5 values. So that explains you have 5 orbital D. Okay? So if you have L equal to 3, that means you have orbital F. You have minus 3, minus 2, minus 1, 0, 1, 2, 3. So basically you have 7 values. So you will have a 7 orbital F. Okay? So you have only one orbital S. So that explains why the S have a spherical, because it have no direction between one. If you have 3 orbital B, because it will arrange on X, Y, and Z. You have 5 orbital D, and you have a 7 orbital F. Okay? So n equal to 1, you have n only positive, L equal to 0. So you have orbital 1s. If you have n equal to 2 at the second layer, you have 2 values, 0, 1. If you have 1, 0, that means you have orbital 2s. If you have n equal to 1, so you have 3 orbital d. Okay? It's quite easy to understand. This one is in your slide already. I will not go more in detail. So to summarize, you have this table. Okay? In the first layer, with the main quantum number n equal to 1, you have only one orbital 1s. In the second layer, n equal to 2, you have orbital s and p. S, you have only one s. P, you have 3b. In the third layer, you will have a S, B, and D orbital. S, you have 1s. 3 orbital B, you have 3 orbital B, and 5 orbital D. In the fourth layer, you will have S, B, D, and F. So basically, in my lecture, you just focus in the second and the third layer. That means n equal to 2 and n equal to 3. So the key element will have S, B, and D orbitals. And more of the interesting chemical property come from the D element. That means the element which have orbital D with electron difference than 0. Okay? That later we call the transition number. Orbital with the same value of n form what we call a cell. That's the concept of ball, right? We have the same layer, same cell. Orbitals that have n equal to 3, for example, are said to be in the third cell. That means you have n equal to 1, the first cell, second cell, and third cell. Orbital with the same n and l value form a subcell. For example, you have subcell 2s, and subcell 3 you have subcell S and B, for example. In the cell number n, there are n subcells, right? So if you have n equal to 2, that means you have 2 subcells S and B. N equal to 3, you have 3 subcells S, B, B. Okay? The total number of orbitals in a cell is n power 2. That means if you have in the first cell, you have n equal to 1, so you have only 1 orbital because n power 2 means 1 square equal to 1. So in the second cell, you have n equal to 2, so in total you will have 2 power 2 equal to 4 orbitals. Actually, you have 1n and 3p, right? In the third layer, you will have n equal to 2 equal to 3 equal to 2, that means 9 orbitals. Actually, you have 1s, 3p, and 5d. Okay? So you see that it is quite easy to understand. So you see that if you try to arrange the orbital in different energy level, because at the end of the day we consider about the energy level, right? So you have 1s, you have 2s, 2b. So basically, when you have the subcell, the orbital will have the same energy level. So orbital 2n and orbital 2b, they have a comparable energy, right? But they have higher energy than n equal to 1. That means higher energy than the 1s orbital. So you see, it's quite easy to understand. Looking at the size of the orbital, so here you have the probability to find electron, right? And here you have the distance from the nuclei to the space around. So here you can see that the highest probability to find electron in the orbital 1s will be here at 1 angstrom. Looking for the case of orbital 2s, you have a high probability to find electron here at over 5 angstrom. But more of the time you will find electron in the distance about 3 angstrom from the nuclei. So you can see that at some moment in orbital 2s, the electron gets closer to nuclei. But more of the time it will stand far from the nuclei with a distance about 3 angstrom. It would say that the orbital 2s will be bigger than orbital 1s. Is it clear? So the same you have here, orbital 3s. So you have a probability to find very close to the nuclei and very far from about 7 angstrom. So let's say that in terms of the orbital size, orbital 1s smaller than 2s and smaller than 3s. Okay? So the same for the 2b, 3b. Okay? So if you have orbital p, because it has 3 orbital b and it's arranged in 3 different directions, so we will have one aligned in the z-x, one aligned in the x, and one aligned in the y-x. So here and orbital d, you have 5. So you see that it will arrange on the 5 different orientations. I invite you guys to look at this and see what could be the orientation. Okay? Can you recognize what could be the orientation? Easy to understand, right? Now, move to the last question. Here is experimental result. If you have a dry cobalt nitrate, there is no colorless powder. When you put water inside, it becomes a pink solution. If you add ammonia inside, it will have a blue solution. My question is, can we explain this phenomena understanding that the cobalt is a d element with the d orbital? Am I clear in my question? First, very simple one. How can you explain this phenomena? That's something we observe, right? If we pick up the dry cobalt nitride, there's no colorless. If you put inside water, you will get pink solution. Okay? And then you add ammonia inside and H3, it will have blue solution. My question is why? How can we explain it? I try to provide example to tell you that all what we learn about orbital are useful to explain experimental data, it will be very useful in our daily life. Not only just for fun and to remember. How can we explain this phenomenon? Anyone? Okay. So, I will go very fast. So basically, imagine that when we have cobalt, we have 5 orbital d, right? And 5 orbital d will be at the same energy level. So all the electron nuclei in this 5 orbital d at the same energy level, they cannot absorb any energy. Because if you want to absorb energy, you need to excite to the higher level, right? Because they are at the same level, so they cannot absorb any energy. So because it cannot absorb energy, so it becomes colorless, right? You cannot absorb energy, then it means you cannot absorb any photon. So all the photon we send through this camera will be transparent. So there's no color, okay? But now, when we put water inside, then 6 molecule water will arrange in this 6 position. Okay? So when this 6 position here will be 6 molecule water, 5 orbital d, now they are not in the same energy state anymore. They split into 2 groups. One group of the 3 orbital at a lower energy level and 2 orbital with a higher energy level. So start from 5 identical, now we have 2 at the higher one and 3 at the lower one. So basically all the electrons localized here can absorb sunlight to excite into the higher energy. So that's why this color becomes color. It's half color, which is the pink color, right? And then when you replace the same thing, but you replace 6 molecule water here by Na3 ammonia. So the difference between this energy and this energy become changing. It will not have the same energy gap anymore. So it will absorb different photon. When it absorbs different photon, it will have a different color. Okay? So that's the matter of changing the level energy orbital. So we call the law of color compensation. It means that if one camera absorbs the yellow, you will see the violet. So if it absorbs here, you will see the violet. Or if it absorbs violet, you will see the yellow color. If one camera absorbs the red, in the red area, you will see the green color. And inverse, if someone absorbs in the orange, you will see the blue. So basically, you absorb one photon, you will see the color of the compensate. Okay? Not like you have the full spectrum you absorb, and you see the color of the remaining one. No. You absorb the red, you will see the compensate, that means the opposite, which is the green. If you observe the green, you will see the red color, but not the old other photon remain. So that is the selection rule if you want. So here is one example for you guys. I want to discuss before we end our lecture. First, can you write the electronic configuration of the molybdenum?
Yes.
And then the second question is that a compound of molybdenum, so the green color, this one. I pick up from my research lab, not imagine anymore, the research lab. And you see that it have a green color because it absorbs the red light. Okay? If it absorbs the red light, you see the green color. What would be the oxidation state of this molybdenum within this compound? Whether it's molybdenum 5 or 6. Okay? So this is something we will have in the midterm and final exam.
No.
Okay?
No.
It's not like write and calculate. You don't need to calculate several things, a lot of things. But I would love you guys to be able to describe this question. So can you pick the photo of the question we will discuss in the next session, okay? Another question, more important before we close. You see that nowadays some high building will have the window, right? And during the daytime, you have the sunlight in the right. So when the sunlight hits our building, the temperature inside will increase, right? So one of the possibilities is that they use what we call the smart window. So in the morning, the window will be transparent like this. You can see the building outside. But then in the lunch time, because the photon becomes stronger, we turn on the smart window, become the green color like this. So you see, we can protect from the sunlight, right? And to make this smart window, they use what we call the electrochromic material, which is tungsten oxide, WO3. Right? Tungsten we have a lot in Vietnam. If someone comes from Thailand, we have a mineral which have a good source of tungsten. Okay. So it's very important source to develop the smart window. So my question is that with your understanding about the electronic structure of tungsten, give an explanation of this phenomenon. Why we start from something transparent, when we turn on electricity, it becomes this color, okay, blue or green color, depending on the potential you apply. Okay, so there are two questions. I will upload this one in the Moodle. So, but better you pick up the photo because sometimes I can forget and take time to upload. And try to work on the two questions. We will discuss this next week. Okay? Do you have any question for today's lecture? Yes.
Okay, so I want to ask this question. Does this phenomenon is like an apply on the window in the plane Boeing 787?
Yes. So the same thing you can find in the window in the airplane, because you don't need to close the window anymore. You just turn on the color will change. Okay. Okay. Any other question? If not, thank you, and please work on that. We will discuss next time. Okay. Thank you.
Xuống học tin phòng Nam.